All right. Looks like majority of people are ready to go, so let's get started here. 6.3. So, like I said, sine, cosine, tan, the trig buttons on your calculator. The way the calculator calculates it is that, well, sine, cosine, tan are actual functions. So if I were to ask you, hey, does the sine graph look like? You can actually graph it. And so you're putting in an x value, the number that you put into sine, the angle is actually an x value that you're putting in, and then you're getting a y value out of it. That's what the calculator is actually doing. So we want to dive into that detail within this unit of what is the sine function, what does it look like, what are the properties, how do I graph it, right? So we are going to dive into those details now that we've kind of done, I know how to do the calculation. So now let's dive into why those calculations work in the first place. So with the sine ratio, when we think of SOHCAHTOA, right? For sine, it's opposite over hypotenuse. And for a sine ratio with acute triangles, we want to possibly determine what if the angle is not 90 degrees? What if it's greater than 90 degrees? So we want to take a look at this situation here. So let's consider a right angle triangle where the hypotenuse has a value of 1. So if the hypotenuse is a value of 1, which is this section right here, right? This section in red. If that is a length of 1, and we call x as x, horizontal as x, vertical as y, we can call the opposite over hypotenuse y over 1, right? So if this is theta, this is opposite, this is hypotenuse, and so our sine ratio would be y over 1, which can be just simplified to sine theta equals y. The reason why this is important is because it relates our sine ratio not to just a triangle. Actually, it relates it to something we call a unit circle. So if we place this triangle on a grid, right, on a Cartesian plane, we have it looking like this. And that means if we were to draw a circle with a radius of 1, we can get any triangle on it, right? Any triangle works for that unit circle as long as its radius is 1. So assuming that the hypotenuse remains constant, the sine function will always be equal to the y value. That's really important. Okay? So the sine function is equal to y when the unit circle exists. So it doesn't matter what the length is. If the radius, I don't know if this, no, I'm trying to draw a circle. Let's see, does that work? I gotta draw it much bigger than that. Give me one. Bigger. This is such a pain to do because it doesn't draw from the center. Yeah, something a little bit smaller. Okay, so something like that, right? So if this red circle is a unit circle, a length of 1, then it doesn't matter how I draw my triangle, right? So if I draw another triangle here over on the left side here, that's not the way I wanted to draw it. Do I have to draw it like this? Yes, I do. Okay. So if I were to draw a triangle like this, or maybe I'll do it in blue, right? And let's say we're starting from the center here. This is still y here, x here, and this is 1. So it's really, this kind of property of this triangle is actually really, really important. Okay? So this property that makes a unit circle really gives us a couple of key pieces of information in math, yada, 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 a lot of history behind it. You'll learn more about it in grade 12 if you take grade 12 functions, advanced functions. where you start diving into something called trig identities, which relates trig to specific math values that you can prove. So here, the angle theta is calculated from this horizontal line upwards this way. It's calculated counterclockwise, which is weird. Most people assume that it's clockwise, but it is counterclockwise, and it goes around the circle. So if this is the case, the trig ratios can be simplified to these three situations here. Sine theta is y over r, which we just talked about. Cos theta is x over r. And then tan theta is y over x. Right? And so this is going to be our our primary trig ratios within a unit circle. The reason why we do this, though, is because the sine function itself is actually limited to two things. Number one, the maximum it could be is 1, and number two, the minimum it could be is -1. So it fits within this unit circle, which is why we're talking about it right now. So when we graph it, you're going to see that the maximum value that the sine function can have is 1, and the lowest minimum value that the sine function can have is -1. And so in this unit, we're just going to be focusing on the sine function specifically. Okay. So now, let's investigate the signs of the sine ratio from quadrants 1 to 4. So do you guys remember where the quadrants are within the Cartesian plane? If I draw like a Cartesian plane here, right? Where is quadrant 1? Anyone know?
Top right.
Top right. Quadrant 2?
Top left.
Yes, top left. And then it goes around in a quarter circle, so quadrant 3 and quadrant 4. So for us, essentially, right, anything in between, we have, if you didn't know, it would be 0 degrees here, then 90, 180, 270, and then back to 360 because it's a full circle. So in quadrant 1, we're looking from 0 to 90. What would the sine be for sine theta? So if we type it into a calculator real quick, we can quickly find the sines for the sine ratio. So we just type in 0 sine is going to give us 0. So that's going to be, we can call that positive. 30 sine is going to give us positive 0.5. 60 sine is going to give us positive 0.866. And sine 90 is 1. Whoopsies, that's cos 90, sorry. Sine 90 is 1, which is positive. We continue onwards here. Sine 120 is positive. Sine 150, positive. And sine 180 is 0, which we can consider positive. Okay? And then from here, right? Actually, let's put zeros inside the 0. Actually, where the zeros are. I think that might be better for us. Let's just put zeros here. So we have 0, positive, 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 0, and 210 would give us negative. 240 would give us a negative number. 270 would give us a negative number. 300 degrees would give us a negative number. 330 would give us a negative number. And 360 will give us 0. Anyone see a pattern here?
The bottom quadrant.
When it gets to 0, it changes the sign.
Yes, and Christian, you said the bottom quadrants are?
Negative and the top quadrant is positive.
Yes. So that's really important here. So where we summarize that, so what Sydney says was every time it hits 0, the signs change, which is a very good observation. And then the second part was that it's the bottom quadrants that are negative and the top quadrants are positive. So if we summarize that in our table below here, this would be positive in the first quadrant, positive in the second quadrant, negative in the third, and negative in the fourth. Okay? So now let's graph it. Okay? Specifically, there are 5 points we can graph. It's kind of hard to graph all of them, mainly because like something like sine 60, if you remember, if you see it on a calculator, can you graph this accurately? 0.8, 0.866. It's kind of hard to graph that, let's be honest, right? It's very, very hard to graph that. And so as a result, we're going to be looking at some key values that's going to tell us some important pieces of information that will help us graph this very easily. Those key points are as follows. It will be 0 degrees, 90 degrees, 180 degrees, 270, and 360. Okay? Those are the important ones. And then the secondary ones would be like 30, 150, 240, I believe, and then 300. I gotta double check that. Let me just do the math here real quick. No, 210. Sorry, 210, and then 330 would be the important secondary ones that will help us graph it a little bit better. Okay, so I'm gonna first draw the first 5 important points, which I circled. So here, every line is 10 degrees on the x, and then of course we go until 1. So if we try to graph this here, the first point when theta or x is 0, we get sine theta is equal to 0. So there's our first point there. We get 0, 0. The 90, at 90 degrees, we hit a value of 1. So when we put it in our calculator here, where did my calculator go? Sine 90 is equal to 1. So when x is 90 degrees, y is 1. So we're going to draw that right up here.
Mr. Choi, when I put it into my calculator, it says 0.98. Do I just round it to the nearest, like?
You should not get 0.98.
I put sine 90. I don't know why it's not.
Check, does it have the words or letters RAD on top of your calculator somewhere?
It said grad.
Yeah, change that to DEG.
Okay.
Or reset your calculator. And that should help. That should fix it.
Yeah, I did fix it. Thank you.
Perfect. No problem. And then at 180 degrees, which is right here, it's back to 0. And then at 270, sine 270 is negative 1. So I'm going to find 270 on the x and negative 1 on the y, which is right here. And then we have 360 is back to 0. I think you guys can see a pattern here. Now, the tendency that people want to do is this. It's like, oh, easy. I'm going to graph it like this. This is wrong. Don't copy this. Do not connect the dots. There's an issue with this. Okay? Because you'll see the second points that I said were important were the stars, the purple stars. So the purple points are actually 0.5. So 30, sine 30 is 0.5. We can graph that there. So sine 30 is 0.5. That's easy to graph here, right there. Sine 150 is also 0.5. And sine 210 is negative 0.5, which will be right here. And then sine 330 is negative 0.5 as well. Now you'll see, if we try to connect the dots here with the straight line, we're going to completely miss that point, aren't we? We're going to completely miss that. Now, I said it's going to be a little bit difficult to graph it, but we're going to do our final graphs, which is in black, the 60, 120, 240, and 300. those are the 0.866 values of our sine function. So if I graph 6 sine 60, I'm going to get approximately 0.866, which is approximately here, I would say. Like approximately there. We try our best. And same thing at 120, around that same level. And then we do the same thing at 210 and 240 and 300, except they're negative 0.866. So that would be down here and down here. Now, if we were to draw this, okay, to the best of my ability, it would look something a little like this. That was terrible. Hold on a second. Give me a sec. Okay, and you'll see it curves down and around. And it's not really a straight line, but rather a curve. So it's a nice smooth curve that looks like this. This is how you graph the sine function. This is legitimately the graph for the sine function. Okay?
Is there?
Yes.
I'm sorry, can you please explain again how did you get the black points?
Yeah, the black points are just plugging in sine 60.
Okay.
So if we do sine 60 here, we get 0.866. So I tried to graph that as best as I could. Same thing for 120, 240, and 300.
Does it matter
So
which order we plot these down in? Like, do we have to do like the purple, then red, then black, or can we just do
no,
the?
it doesn't matter. You can do it in order. I did this like this because when you start graphing this, or if I were to ask you, how do you graph this quickly? The reason why I did all the points is to show you, hey, it's not straight lines, right? It's not a straight line. It's going to be a curve, right? Once you know that the key points are these ones here, the red dots, you don't really need to draw the rest. You can kind of just connect the dots into a nice curve, right? As long as I don't see straight lines, I'm okay. So the main point of drawing everything here, doesn't matter which order, is to show that it's more of a curve than a straight line. Are there arrows at the ends? Good question. Usually for the sine function, we don't draw arrows. We do have it like continuously going onwards because this is periodic. We know that the sine function is periodic, so we know it goes infinitely. So usually the sine function, we don't draw arrows, but it is a good habit too. But most of the time we're looking at a specific section, so it should be fine. All right. Anyone want to answer? Is this curve a function? Yes or no?
Yes.
Yes. Why?
Yes.
It passes the vertical line test.
Perfect. Back to unit 1. It passes the vertical line test. Right? The vertical line test was like passing a pencil, vertical pencil, or an object from left to right. As long as it only passes through one point of contact, it's a function. So this is definitely a function, which is why I have been calling it a sine function. Right? So now, the difficult part. Domain and range. If we specifically look at this section only, let's get this practice. I want everyone to try finding the domain and range for the sine function on your own. I'll give you 2 minutes to do so. All right. And then we'll check your work here. Okay. Assume that we're looking at this section only. Otherwise, the domain would be XER and that's it, because it goes infinitely both ways, like Brooke was asking before with the whole arrowhead part. But let's assume that we're only looking at this section. Can you give me the domain for this section only? Okay. I'm going to try to redraw my ugly sine curve here. Ugh. I do this so much better on paper. Okay, that's good enough. That's a passable mark, right? Right, guys? Okay. Your domain and range should be complete. Domain for the sine function that you should have, I'm going to zoom in a little bit here, will be XER, X is any real number, such that 0 is less than or equal to X, which is less than or equal to 360. So the lower limit is X is 0, and the upper limit here for this section is 360. So that should be your domain there. Okay. For your range, YER, such that -1 is less than or equal to Y, which is less than or equal to 1. Because the Y value goes as low as -1 and as high as +1. And it's not go anywhere further than that. If you wrote this as your domain and range, congratulations, you did very well. That's exactly what we want. Okay? That's exactly what we want you to know and remember as you dive into this. So be prepared to write domain and range if you see something, right? If you see like a word problem, which we'll go into in a second, you should be able to identify the domain, the range. Is it a function? Is it not a function? Explaining why, all that kind of stuff. Okay. Any questions about this?
Why is it 1 and -1 again?
The Y value goes as low as -1, as you can see here, the lowest point, and then the highest point goes as high as only +1. It doesn't go any higher or lower.
Okay.
Okay. Any other questions?
Mister,
Yes.
can I ask you a question about this after the class? Because I'm
Yep.
a little bit confused about the domain and range.
No problem. Yeah. Okay. Then let's continue onwards here. These are some important terminologies. You probably want to make sure you understand this for the quiz. Make sure you have this ready for your quiz, right? Because these are some important terms to identify key pieces of information about your sine function, about a periodic function. So obviously the sine function is this important part right there. And I'll box it out with a rectangle where f of x is equal to sine x. That's essentially what your sine function is. So when you do it on a calculator, your calculator is using this function and spitting out numbers using that. Okay? It is a periodic function. We know it repeats. It constantly goes up and down like a wave, so on and so forth. Now, a sinusoidal function is a type of function that is created by transforming this function here. Okay? So when you look at another graph and you're like, oh, that kind of looks like a sine graph, but it's not obviously the sine graph, then it's called sinusoidal. It looks like a sine graph. It behaves like one. We call that sinusoidal. So because it goes up and down, another thing you should be able to realize, even from what we've drawn here, is that it almost looks like not symmetric, like it looks symmetrical in a sense, where you can cut this straight down the middle. You know where the upper part is that we said was positive. We know where the bottom part is where we said it's negative. So there's gonna be this portion of the graph that's the middle of your sine function. So here, the middle of this sine function would be this red line here, right? If we look at this example here, right? It's that middle line. That's going to be the equation of the axis, right? And so that's going to be the center of our sine function. That's really important for you to identify for a future lesson. And the formula for it is this one, is this here. This is the formula, okay? And in case you didn't realize that, that's the formula. Okay, so that's how you get the equation of the axis using this. You take the maximum value of the function plus the minimum value of the function and divide it by 2. So that's going to be the equation of the axis. It's exactly halfway, right? The amplitude, that is a word that you hear not just in math, but I'm sure you've heard it in like music as well as some other things, right? Amplitude in music or sound is like volume, right? How loud something is. And sound is actually a wave. So the amplitude is actually just telling you how big the wave is, right? So if I ask you, oh, what's the amplitude of a wave? It's asking you, oh, how high does the wave go? And because the equation of the axis is halfway, you calculate the amplitude from the middle to the highest point. So this would be the amplitude there, right? And it doesn't matter which direction you go, up or down, the amplitude would be exactly the same. So how high or how low does your sine function go? From the middle line, the equation of the axis.
Wouldn't it be the same number as a max or min?
No, not always. It would be if it was at 0, but then in different word problems, you're not always going to get it at 0. So we're going to see an example of where it's not doing that, and we'll go into that. But that is a very good question. There is a way you can also calculate this with the maximum minimum. So I'm going to give you that formula here because it's not written down, where the amplitude is equal to max minus min divided by 2. Okay? Not to get confused with the equation of the axis, which is max plus min divided by 2. The amplitude is max minus min divided by 2. Okay? So this is your second formula that you want to oopsies, I was supposed to make a rectangle. Yeah. So this is your second formula. Have that written down. It will be very helpful for you when you determine the amplitude in the case that it doesn't start or the equation of the axis is not 0. So let's go through an example here of the regular sine function. And on page 4, you'll see an example where it's not it's a sinusoidal function, and you're going to identify those key pieces as well. So this is technically 6.4. So we're going to dive into this here. Looking at here, what is the period for the sine function here? And you remember what the period is? The period is how long does it take for it to repeat?
360.
Perfect, 360. Hit the period is 360. It goes from 0 to 360, and if we kept drawing, it would keep going, right? Whether it's forward or backwards. So 360 would be the period. What's the maximum value? What's the highest it can go?
1.
1.
1. Minimum is?
-1.
1.
Perfect. What's the equation of the axis?
Maximum value plus minimum value divided by 2.
0.5.
Good. So 1 plus -1 is?
0.
0. 0 divided by 2 is?
0.
So y equals 0 is the equation of the axis. Okay? So the equation of the axis, because it's an equation, we have to put y equals 0. Don't just put 0, right? You'll notice in the formula, it says y equals. There's a reason why that's there. So we want to write y equals 0 as our equation of the axis.
Mr. Choi, I have a question. For the minimum,
Yes.
like when I look at it, does it not end at like -0.9? Because the actual graph doesn't reach -1.
It should reach -1. See?
Oh, that's weird, but like I don't know, maybe mine printed out weird or something.
It might just be visually, it looks like it doesn't, but it should hit -1. Yeah. And then for the amplitude, what's the amplitude here?
1.
1. Because to get to the top, it's a height of 1, and to get to the bottom, it's a height of 1. Okay? So you'll notice in both ways, the amplitude is 1, right? From the center. So 1 up and 1 down. So you just take positive, which is 1. Okay? So that's pretty easy. That's for a regular sine graph, right? No changes, just a regular old sine graph. But what if we get something like this? Sarah is sitting in an inner tube in a wave pool. The depth of the water below her in terms of time can be represented by this graph. You can see this is sinusoidal, right? Because it's not the sine graph, but it looks like one, right? It behaves like one. So let's take some time to do so. I'm going to give you 3 minutes to fill out this piece of information. You need to find the period, find the maximum height, find the minimum height, the equation of the axis, and the amplitude. All right, 3 minutes. Okay. Anyone want to give a shot at this? What is the period?
3.
3 is correct. 3 seconds would be the period here. Now that we have units, so 3 seconds, right? From here to here would be repeating. So that's 0 to 3. Perfect. What's the maximum height?
2.4 meters.
2.4 meters. Minimum height?
1.6 meters.
1.6 meters. Equation of the axis. Y equals?
I got 1.9. Not sure.
1.9? No, not quite. It should be a whole number, not a decimal. 2. 2 is correct. Brooke wrote 2 in chat. Yes, y equals 2 is correct. So max, y equals max plus min divided by 2, which will give us 2.4 plus 1.6 divided by 2. That gives us 4 over 2, which is 2. Right? So we want to use the formula to our advantage here. You can also kind of see if I draw a horizontal line in red right across here, you'll notice that's exactly the middle at y equals 2. And the last one, the amplitude.
0.2 or 0.25.
I heard 0.2, which is not right.
Is it 0.4?
Yes, Kimberly and Lorraine have it, which is 0.4. That is the amplitude. You can see it from here, from the middle. This height is 0.4, and same thing here, that's 0.4. The other way you can calculate it, once again, is to use the formula. Amplitude is max minus minimum divided by 2, which will give us 2.4 minus 0.6, or sorry, 1.6 divided by 2, which gives us 0.8 divided by 2, which equals to 0.4. Okay? So your quiz will entail just having you fill out some information about if I give you a sine function or a sinusoidal function, can you give me the according pieces of information for that function? Otherwise, that is the lesson for today. Make sure you do your homework. Make sure you practice for your quiz tomorrow. Once again, I will be absent tomorrow, so if you do have any questions, it's best for you to ask me now or forever hold your peace, or just send me an email and I'll try to respond before tomorrow. Otherwise, that is it. Have yourselves a wonderful rest of the day.